Hey everyone, and welcome. Today we're going to tackle fluid statics. Now that might sound a little complicated, but it's really just the science of fluids that are sitting still. And to really get our heads around one of its biggest ideas, pressure, we're going to start with something that, well, doesn't seem like a fluid at all.
All right, so let me throw a question at you. How is a solid concrete pillar, like a deep lake? I know, it sounds a little weird, right? One's totally rigid, and the other, flows all over the place. But stick with me, because by the end of this, you'll see they're connected by this one single idea that is absolutely central to physics.
Okay, first section, from pillars to lakes. So, to crack this puzzle, let's start on, well, solid ground. We're going to look at the forces happening inside something we can all picture super easily, a big, solid pillar.
Okay, let's really think about this pillar. Imagine you could shrink down and become a tiny little speck of dust right inside that concrete. What would you feel? You'd feel the weight of all the concrete above you just pressing down, squeezing you. That internal squeezing force, that's what we call compression. And it makes sense, right? The more stuff piled on top of you, the bigger the squeeze.
So the big question is, where is that compression the absolute strongest? Let's just walk through the logic here. First, let's just imagine a little slice right at the bottom of the pillar. Okay, so that slice has to support its own weight, obviously. But, and this is the key part, it also has to hold up the weight of the entire pillar sitting on top of it. So what does that mean? It means the compressive force gets bigger and bigger the deeper you go. It's at its absolute maximum, right at the very bottom.
Okay, now here's where it gets really cool. What happens if we take that exact same idea and apply it to something that isn't solid? What if our pillar wasn't a pillar at all, but a column of water in a lake? The water molecules can flow and move around, sure, but that basic principle? It doesn't change. The water at the bottom still has to support the weight of all the water piled on top of it. And just like that, we've built a bridge from solids to fluids.
All right, section 2, the nature of pressure. So before we can go any deeper, we've got to make sure we're all speaking the same language. Let's lock in some key definitions.
So first up, what even is a fluid? Super simple. It's anything that can flow. That means liquids, like water, obviously, but also gases, like the air we're breathing. The big difference from a solid is that the molecules aren't all locked into place. They can move around, which is why fluids can take the shape of whatever you put them in.
Okay, now if you zoom way in, we all know a fluid is really just a bunch of individual molecules bouncing around with empty space in between. But for most of what we do in physics, on the scale that you and I live in, that's way too complicated. So we make a really useful simplification. It's called the continuum assumption. We basically agree to pretend the fluid is a smooth, continuous stuff with no gaps, and you know what? For describing how it behaves overall, this model works beautifully.
And that brings us to the star of today's show, pressure. So what is it? Pressure is just the amount of force a fluid pushes with divided by the area it's pushing on. You'll often hear it called thrust per unit area. And for a fluid that's just sitting there, not moving, this force, this push, is always straight on or perpendicular to whatever surface it's touching. That's a super important point. Okay, this next bit is something that trips a lot of people up. We just said pressure involves force, and we all know force has a direction, so that must mean pressure is a vector, right? Well, surprise, the answer is actually no. Pressure itself is a scalar. It just has a size, a magnitude, it's just a number at a particular point. Think of it like the temperature in a room. It's 20 degrees right here. It doesn't have a direction. Now, the force that results from that pressure, that's the vector. And its direction, it's determined by whatever surface it's acting on. The force always points perpendicular to that surface. So remember this, pressure is the how much, and the surface tells you which way the force goes. Okay, third section. Pressure's vertical climb. Now that we've got our definitions down, let's put them all together and figure out the #1 rule of fluid statics, how pressure changes as you go deeper.
And look at that. We're right back where we started with our pillar. It's the exact same idea. Just like the bottom of that pillar has to hold up all the concrete above it, a layer of water deep down in a lake has to support the weight of all the water above it. That is the reason pressure changes.
So how do we get to a formula for this? Let's build it step by step. First, just picture an imaginary cylinder of water floating in the lake. Okay, now what forces are acting on it? Well, pushing down, you've got the pressure from the atmosphere on top, plus the actual weight of our water cylinder. And pushing up from the bottom, you've got the pressure from all the water below it. Now, since our little cylinder isn't sinking or rising, it's in equilibrium, the upward force has to exactly equal all the downward forces combined. And that simple balance is where the formula comes from.
And boom, that force balance gives us this, the fundamental equation of fluid statics. P equals P naught plus rho GH. Let's break that down. The pressure P at some depth h is equal to whatever pressure you start with at the surface, we call that P naught, plus this extra term, rho GH. That's the pressure caused by the weight of the fluid itself. Rho is the fluid's density, G is gravity, and H is how deep you are. This formula is your best friend in fluid statics.
So you might notice that rho GH only cares about the vertical depth, h. Why is that? Well, it's because of something called a pressure gradient. A gradient is just a fancy word for how fast something changes as you move. In a still fluid, the only thing causing pressure to change is gravity, which pulls straight down. So you only get a pressure change when you move vertically, up or down. If you move side to side horizontally at the same depth, the pressure stays exactly the same, no change.
All right, last section, the power of the gradient. Now, I know it might look like just another formula, but trust me, getting your head around this vertical pressure gradient, it is the key. It unlocks pretty much everything else you need to know about fluids that are sitting still.
I mean, just look at this quote. The simple fact that pressure increases with depth is the key that unlocks almost everything in fluid statics. Seriously, if you take one thing away from this, let it be that. This one idea is the master key to it all.
Think about it. This one idea explains so much. It explains buoyancy, why things float. The pressure at the bottom of an object is stronger than the pressure at the top, so you get a net push upwards. It's why massive dams have to be way thicker at the bottom to handle that incredible pressure from the deep water. It's how hydraulic lifts can multiply force. It's even why atmospheric pressure drops when you climb a mountain. You're just putting less air on top of your head. It's all connected.
So, there you have it. We've pretty much mastered the basics of a fluid at rest. We have the tools to figure out what's going on in any fluid that's in equilibrium. But that leads to a pretty interesting question, doesn't it? Everything we talked about today assumed the fluid was just sitting there. So what happens when it's not? What happens to all this pressure stuff when we start moving the fluid, when we accelerate it? Well, that is a story for next time.